Namaste children, welcome to the next session 5 of real numbers. Okay, we are continuing with our sums in exercise 1.1. Till last session we did about the HCM and its applications. Okay, now we are moving into the characteristic representation of a number using division lemmas. Sums are based on this. Okay, we'll try the second sum. Show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5 where q is some integer. Okay. Now I have told you in the beginning itself, any number can be written in the form a is equal to bq plus r where r is greater than 0 or equal to 0 but less than b. Now here the question is any positive odd integer, we don't know what it is, okay, is of the form 6q plus 1. So we are not going to take as odd integer, we are going to take any integer can be written in the form 6q plus r. So where r should be between what? R should be between 0 to, so as r can take the values from 0, 1, 2, 3, 4 and 5. 5 values R can take. 1, 2, 3, 4, 5, 6 values it can take. Okay. It can be 0, it can be 1, it can be 2, it can be 3, it can be 4, it can be 5. Logically, if it takes the value 6 means what? The whole number will become a multiple of 6. Okay, so we are restricting to up to 5 only. That is the fact. Okay, and this kind of representing a number is based on Euclid's division lemma. Okay, now whenever sums of this type comes, we have to analyze from case by case. First case, case 1, it is r equal to 0. Now when r is equal to 0, what will happen? A is equal to 6q plus 0. When a is equal to 6q means it can be written as 2 times 3q, that is 2 times a multiple. We can say it is m. Some number, m is only a representation. You don't go by the value of m. It is 2 times some representation of a number. Okay. Therefore, what do you get? It is an even number. When you are able to write a number as 2 times some other value means it is a multiple of 2. Therefore, it is an even number. So, this gives even. So, I don't want this. My solution is for odd integer. Let us see next case what happens. Then we have to go for case 2. We will get r equal to 1. When r equal to 1, what happens? We get 6q plus 1. Obviously, 1 is the remainder, means this number is nothing but 2 times some number plus 1. 2 times some number plus 1 means it is odd integer. So, in order to indicate that you have to get the correct answer, you can have a tick. To analyze the case when r is equal to, we can write here case 3. So, case 3 is what? R is equal to, we have finished 1, it is 2. Therefore, your a is equal to 6q plus 2. 6q plus 2 what? This is a multiple of 2. This is a multiple of 2 again because 2 into 3 times. Therefore, the whole thing is a multiple of 2. Therefore, what do we get here? It's even, which we are not considering. Okay. Next, we should go for case 4. So, case 4 is what? R is equal to 3. When r is equal to 3, what will happen? You get the number to be 6q plus 3. Now here I can split as, why I have to split? I want to test for odd numbers. Therefore I have to split plus 1. Therefore you get 2 times, we can take it out, 3q plus 1 plus 1. That is 2 times some m plus 1. That means what? When r equal to 3, we are able to write the number as 2 times a number plus 1. That means what? It is an odd number. That is when r is equal to 3, when it is of the form 6q plus 3, you get an odd number. So we are considering, therefore I put a tick there. It is okay. Alright. Next, Next case we have to see r is equal to 4. When r equal to 4, what will happen? A is equal to 6 cube plus 4. So I am taking out 1, 2, 3 cube plus. That means 2 times some multiple, isn't it? When you write 3 into 2 cube, 3 cube plus 2 means 2 into, we are able to write it as some multiple of 2. Therefore, we get 6 cube plus 4. Are you understanding? That means in this case, what number you will get? You will get an even number which we are not considering. Last case, r is equal to 5. Let us see r is equal to 5. Can you tell the answer? It is nothing but a is equal, I will write here, r is equal to 5 means you get a is equal to 6 times cube plus 5. Now in order to have the 2m plus 1 form, we can split it as 6 cube plus 4 plus 1. I am bracketing these two. Now here we can take out 2. So you will get 3 cube plus 2 plus 1. That is 2 into m plus 1. We are able to write a as 2 times the number plus 1. That means what? In this case also we get an odd number. Therefore, that is what we want. Okay. Okay. Now analyze all the cases. In 5, 6 cases, when r equal to 0, we get even number. When r equal to 1, odd number. When r equal to 2, you get an even number. When r is equal to 3, you get an odd number. When r equal to 5, you get an odd number. So, considering all these calculations, what can we sum up? Therefore, any odd positive integer can be written in the form 6 cube plus 1, 6 cube plus 3, 6 cube plus 5. Okay. Continuing with the fourth sum, you have to use the same Euclid's division lemma for proving this sum also. Okay, let us read the sum. Use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer value m. Okay. Now how do we do that? You all know that any integer can be written as a. Any integer a, it is 3 times a number plus r. Now how do we get 3 here? Because I have to get in terms of 3. As a multiple of 3. That's why I use the number 3. Okay, it is possible. We have seen it already. Now here r can take the value 0, 1 and 2. So I will write r can take the value 0, 1 and 2. 3 cases you have to analyze. So I write the statement as 0 is less than or equal to r is less than 3. Are you understanding? So we have rewritten an integer in the form 3p plus r, and this is how we have to proceed. Now let us take for the first case 1, a is equal to 3p plus r, where r is equal to 0. When r equal to 0, what will happen? You will get a is equal to 3p and a square is equal to 3p the whole square. You will get 9p square. That means it is 3 into 3p square we can write. What does it indicate? It is 3 times a number. Correct? Therefore, it is a multiple of 3. Or you understand, the square of the number can be written as when r equal to 0 in the form 3 times 3p square. That means 3 times a number. Some number. 3p square is obviously an integer. Correct? So it is 3 times a number. Therefore, your first case is proved. You can put a tick here. Now come to the second case. Second case is what? R equal to 1. Therefore, a is equal to what? 3p plus 1. A square is what? Using a plus b the whole square, it is 3p plus 1 the whole square, which is 9p square plus 1. 3p into 2, that gives you 6p. Now I am separating that 1 to that side, 9p plus 1. Okay, therefore this 2 I am bracketing. So we can take the 3 out. So you will get 3p square plus 2p plus 1. What does it indicate? It is indicating that the square of any integer can be written as 3 times a number. 3 into something means 3 times a number plus 1. Okay, 1 will be left over. So what do you get? You will get 3m plus 1. So this is fulfilled. Okay, we have verified the case for r equal to 1. It can be written in the form 3m plus 1. But do you think that the sum is over? No. We have got to analyze one more case. What is it? You write r is equal to 2. So in which case, what do you get? You will get a is equal to 3p plus 2. Therefore, a square is equal to 9p square plus 4. Middle term, it is 3 2s are 6p into 2, 12p. Then that can be splitted as, it is 9p square plus 3 plus 1 plus 12p. I am separating that 1. So you will get 9p square plus 3p plus 3 plus 12p and then plus 1. You will get, taking that 3 out, 3p square plus 1 plus 4p plus 1, that is ultimately reducing to the form 3m plus 1. So what happens in all the 3 cases? We are either getting 3m form or 3m plus 1 form. So you have to sum up your answer. The square of any positive integer can be written as 3m or 3m plus 1 for some integral value or for some integer m. This is how you should complete the sum. Are you understanding, children? This is how you should complete. And today or in the next session, today we have done all these applications for square and then for simple numbers, odd and even, and also we have done the square form. Next we have to do the cube form, which we are going to do in the next session. Thank you, children. Wish you all the best.